The last thing to talk about for this class is eigenvectors and eigenvalues. So the eigenvalue problem states that sometimes for some matrices, when we multiply a vector times a matrix, it appears as if we just scaled that vector. So I have a basic example over here with 2x2 systems or 2x2 matrices. So let's say I have a matrix A and I multiply it by some vector of x values, and I end up with this vector here. So I essentially took my 1, 2 vector and I transformed it so that it ended up at 7, negative 6. So I've just used this matrix to move this vector over here, and that's fine. However, sometimes some vectors, so here's the same A matrix, here's a different vector, and here's my result. Where over here, it appears as if I just multiplied my vector by 3. It appears I've just said, hey, x times 3. When in reality, I actually multiply it by a full matrix. And that is my eigenvalue problem. Problem in the sense of like mathematical problem. Not problem as in the sense that like I don't want it to occur. So some vectors just appear as if they've been multiplied or scaled by the matrix along the same line versus having been moved to another space, another location in our space. So we want to figure out what vectors these are and what scalar value it appears to be. So x in this instance, these are my eigenvectors. And this lambda, these are my eigenvalues. Okay, so my goal with these, essentially setting everything up, is to find my lambdas, my eigenvalues, and to find my x's, my eigenvectors. So if I rewrite this equation, I just pull ax minus lambda x equals 0, I factor out an x, and here's my equation I'm working with. So note, this is a homogeneous system. And for a homogeneous system, I have two options. I either have a consistent system with a unique solution, or a consistent system with an infinite number of solutions. And it turns out, as we noted in our last video, that if I have one solution, then that solution is equal to x equals 0. It's a trivial solution. I don't care about that one. I care about the infinite solutions to this equation, because then I have some non-zero values. So I want the non-trivial solution. That's just some background, setting things up. So first thing we need to do, use this equation to find my eigenvector, or my eigenvalues, find my lambdas. The way I do that is I'm going to force my determinant to be equal to 0. Because if my determinant is equal to 0, that means I have an infinite number of solutions. So I just solve this equation for lambda. I know what A is, I know what identity is, I know what 0 is. So I just solve for what lambda values make my determinant equal to 0. You can also do this in MATLAB using the eigen function. But that's how we can find our eigenvalues. And we're going to go over examples of this. Our eigenvectors can be found by plugging in our eigenvalues and solving this system. So note, we are going to have an infinite number of solutions. Because we make sure that our determinant equals 0. So we figure out which lambda values make our determinant equal 0, plug each of those in to this system. We use Gauss-Jordan elimination in order to find our eigenvectors to solve the system, just because we know we're going to have an infinite number of solutions, and it's just easier to use Gauss-Jordan elimination. When we find an infinite number of solutions, that means we're always going to end up with at least one row of zeros by the time we find our REF. And so what we do is when we write our system of equations at the end, so we'll end up with something like this. We write our system of equations still. So this one just tells me that x3 equals x3. It tells me that x3 is my free parameter. This one here will give me something x2 in terms of a function of x3. And this one will give me x1 as a function of x3. And what we do is we typically pick one set of solutions. So we pick a number for x3, say x3 equals 1. And then we solve for x2 and we solve for x1. And that will give us one of our eigenvectors for the eigenvalue. And this just describes that process.